Thank you. Thanks, Jeff. It's a huge honor to be here. If I can, okay, here we go. To share our vision and thoughts about radio technology evolution toward beyond 5G and 6G. First of all, congratulations, Jeff, and at UT for the launch. Oh, sorry. You're good now. You can walk away. Oh, okay. For the launch of the 6G center here, especially from this group, WNCG. You guys are really one of the best wireless groups in the nation, probably the whole world as well. Made a lot of fundamental contributions over the years, especially to 4G, 5G, millimeter wave channel model, stochastic geometry, network analysis, joint communication and sensing, and also recent push. I think you guys are probably one of the first group in the wireless area to talk about the application of AI technology and trying to bring them to the wireless area as well. So lots of good applications and good contributions in terms of technology to 4G and 5G, and not only influence the research community, but also through these technology, as well as wonderful students. You guys produce so many good students. Some of them are with us in Samsung, and I'm sure some of them are with some of the affiliates here as well. So really influence not only the research community, but also the standards and industry as a whole. So really appreciate your contribution. And with the new center, I really look forward to the continued success. Let's build the technology together for the 6G era. So before we think about next generation, right? So it's important to look at where we are today in terms of 5G. 3 years ago, about April, exactly 3 years ago, we launched 5G commercially. So things are going pretty good right now. So if you look at a few of the key numbers, for example, the adoption number. So right now, the prediction is sometimes this year, we're gonna hit 1 billion mark. That's a billion with a B. That's a huge number because compared to what we did in 4G days, it took about 6 years to get to that number. So we are 3 years ahead in terms of the adoption of the 5G technology. Then you look at the deployments, right? So especially in these advanced markets, for example, United States, Europe, Japan, China, Korea, things are also picking up pretty fast. In the United States, we already reached, I would say, nationwide coverage in those low bands, you know. But then in mid bands, in 2-3 gigahertz band, we're also getting there. I think sometimes by all the three big operators, they're putting a lot of investment and resources on that. The number I saw is sometime this year, we're gonna be able to hit 200 million mark. So about 2/3 of the population will be covered by 5G in mid-band, which is where the capacity and also a lot of coverage will be. So things are doing pretty great. Then of course, a lot of this wouldn't have been possible without the standardization. So let's take a quick look at where we are in terms of 5G standards, right? 5G, as many of you know, started from something called Release 15. So in the community, we recently finished what we call Release 17. So you can think about Release 15 to 17 is really a first basket of initial 5G standard specifications, really allow this technology to be commercialized at a global scale, right? So, you know, a lot of optimization is going on, but recently one big event that's happening, which is the launch of Release 18. With that, we also changed a marketing term a little bit from 5G to 5G Advanced, right? So there's a few key things that we are thinking that we need to, you know, address, especially during the 5G Advanced days. One is really we're gonna try to build additional tools to allow 5G to be better used for different verticals. Because 5G initially, I think as we roll out, still initial users, initial success, we see a lot in what we call EMBBs, human users, but now we are trying to grow more into verticals. Another thing is, through the initial commercialization, we also have learned a lot of lessons. So now it's a good time to look at some of the lessons and try to address the issue that we saw that's important. For example, the coverage issue that we saw in millimeter wave, very exciting technology, but because of high frequency, coverage is somewhat limited compared to the lower bands. So we are looking at that and see technology to address that. Actually, not only millimeter wave band, but also the mid-band in 3.5 gigahertz, we saw similar issues. So that's why technologies such as, later I'll talk about XDD in some of the new advancement in duplexing technology could be very helpful in addressing the issues. I mean, there's other lessons we learned. Interesting thing, for example, in 5G, one big push when we were developing those standards is trying to make 5G more flexible. We learned a lesson from 4G because 4G is, as a lot of you know, is very, very much hardwired, very inflexible, very efficient, but not very flexible. But as we try to address that issue in 5G days, we probably overcorrected. We made it too flexible. So why is it a problem? Because once you make it too flexible, then you increase the cost for operation, management, and so on. So we are looking at all these and taking into account and try to address them in 5G Advanced. And some of them will naturally go into 6G as we think about the new technology from the ground up. So if you take things back and more holistically look at what's happening in the evolution of the cellular technology, right? It's already been 5 generations, and really the global sort of awareness of these wireless generations started more, I would say, from 3G. That's where data and voice become more integrated, and 4G gave us more LTE broadband. 5G, if you were to say, maybe one thing we really want to push is verticals and make them more customizable for different industries. I wouldn't say we completely achieved that goal. It's still work in progress. If you look at the 3 pillars, at that time we mapped out eMBB, URLLC, as well as massive IoT, right? So I would say we are doing pretty good in terms of eMBB, but on the other 2 areas, still work in progress, right? So then you think about 6G, what can we do? Probably some of what we can do is 5G provided, for example, the inspiration and vision for massive IoT. Definitely, I think 6G will be a good time to really for us to think about technology to take us to this hundreds of billions of device connectivity of the future. Then also, if you look at some of the new emerging applications and use cases, so everybody is thinking about digital twin and hologram and immersive AR, VR, XR, right, today. So these are really what's driving some of the thinking, at least from a technology group, that we're looking at these new use cases, right? For example, if you think about digital twin, it's really interesting. You can't think of it just as eMBB or URLLC anymore. You really have to think about together, right? It's one application that really requires very high throughput, in the meantime, low latency, probably as well as joint communication and sensing. Everything has to be integrated together to deliver the seamless experience that you would need in order to make this a reality toward the end of this decade. So these are really the thinking behind a lot of these requirement discussions that's taking place. That's what we normally do. We think about these use cases. We think about what's really driving these numbers going forward, right? So then, I mean, some of it is still early discussion, but we put together some KPI numbers. Some of them are performance numbers, naturally, the peak throughput, terabit per second. Is it enough to support mobile hologram? Still probably not there, but I think it's a good step forward, right? So then in addition to these performance numbers, we're also looking at changes in network architecture, changes in the security and trustworthiness, right? Especially if you think about going to 6G, it's not only for human communication, but also for machine, right? A lot of inputs, a lot of information that's out there. The openness is good, flexibility is good, but security threat is higher naturally. Because now you're talking about billions, but not billions anymore, hundreds of billions of devices out there in the open. So that's why when you think about 6G technology, it's not only for radio, but we have to think about security and privacy from the very beginning. So, of course, these are the motivating use cases when we think about building the new technology. Then we look at requirements. Then from there, we see a few very promising technology emerging during the time over the last years of, last few years of discussion. So naturally, the new spectrum, thank you. New spectrum is very important. Wireless research and development always starts from new spectrum. So here, 4G is like that. 5G, famously, we talked about millimeter wave. We also later talked about 3.5 gigahertz midband. But here we are looking at, really two areas. One is somewhere above millimeter wave, what we call sub-terahertz, and also upper midband. Then we're looking at a list of technologies covering AI native design. I think really 6G will be the time for AI to really shine. AI is already used today, a lot of 4G, 5G applications. We'll talk about this a little bit more in the later slides, but 6G, we have a chance to really build that in a more native and integrated way in the design of the protocol stacks, right? So then we think about antenna technology, new topology, for example. NTN, non-terrestrial, is already starting in the really 17, 18 discussions, but I think we really think during the 6G days, we really see good optimized solution for these new topologies, for LEO satellites, and so on. So the list is a little bit long, but the key thing is these individual technologies are very important, very exciting, but really to achieve all these requirements that we talked about a little bit earlier and to support these exciting use cases, all of them we imagine they will have to work together as a whole to support all these use cases and requirements. So maybe the first thing to talk about is really the spectrum, right? So 5G, as I mentioned, a lot of people heard of millimeter wave, right? Millimeter wave, by some definitions, from 24 gigahertz to 92 gigahertz, and most commonly used ones are from 28 and 39 today, right? That's a very good band, lots of spectrum, good capacity layer, right? So still, I think deployment is ongoing. We'll see how it goes. There's some early sort of a challenge in terms of coverage, but as I mentioned earlier, 3GPP and industry also looking at ways of improving that. Another very important band that we looked into during 5G days is a mid-band, okay? So at 3.5 gigahertz especially. So, but going forward, in 6G, we think it's also very important. From the very beginning, we need to think about what are the new bands we're going to target. Of course, as a technology, as a generation, we're going to cover the existing bands, just like what we did in 5G, right? 5G expanded into these mid-band and millimeter wave band, but also technology-wise, it's agnostic. It also applies to those existing bands. So here in 6G, we think sub-terahertz and upper mid-band in 7 to 24 gigahertz will be very important. If you look at 7 to 24 gigahertz, that's kind of a sweet spot, right? It has a pretty large amount of spectrum still available, and because it's a little bit lower compared to millimeter wave, so we expect this can provide very good capacity, but also with reasonable coverage. Then definitely there will be question on what are the key driving technology for that. So that's what we need to look into, right? Maybe one, of course, obvious dimension is to think about to scale up the MIMO technology. Because we know, for example, in 5G days, for C-band, for mid-band, the massive MIMO or FD MIMO is really the key enabling technology to provide capacity necessary. So maybe we need to scale that, but is there something else? So that's something we are looking at. And then terahertz, of course, that's even more bandwidth up there, but also more challenging because path loss is even higher in those bands. Okay? So we need to address some of that. But another thing good about these sub-terahertz band in the up there is as you go up in those frequencies, right, this not only provides enormous amount of bandwidth for communication needs, but also in those bands, it's very suitable for joint communication and sensing because large bandwidth naturally gives you better spatial, this range resolution, right? It's a reciprocal for the bandwidth you have. Also, because of the wavelengths get so much smaller, then you really have a chance to pack a lot of antennas in a small form factor devices. So what that means is it's going to give you not only very good range resolution, but also very good this angular spatial resolution. So together, it can be a very good foundational sort of a technology for the future if we really want to think about integrating communication and sensing together. So a little bit more for the upper mid-band. So you can see, right, really what we see is if you holistically think about how the future of the wireless network will look like, they're going to be sitting across all these bands. Mid-band and lower band will provide nationwide sort of a global coverage. And some of the new bands like 6G upper mid-band, they'll also be a national deployment, provide good coverage and reasonable coverage and good capacity. But then millimeter wave and also the terahertz band will be providing very important capacity layers, hotspots, and also other use cases. For example, at terahertz spectrum, we can imagine some of the applications such as FWA, such as backhauling, very suitable for that. Okay. Of course, lots of challenges, even for this band. We are just actually starting to look into this, but naturally, there's a higher path loss compared to the mid-band that we looked at in 5G. There's a lack of the existing ecosystem that provides all these necessary RF components, RFICs. So a lot of work left for us to do together as a community to really allow this to happen in the next few years and for commercialization during the end of this decade. This is if you really want to know some of the details, this provides a little bit more detail of what's really happening in the 7 to 24 gigahertz band. You can see it's pretty crowded already, but the good news is, if you look at the first line, those blue lines, that's those areas that's kind of designated as a primary use of the mobile service as well as fixed service. But the tricky part is, even though this is primary use, it doesn't stop the other use cases down here in the other rows. So I think that will be a lot of discussion in the next few years as we look into this bands for potential 6G deployments. How do we coordinate with other industries, okay, to make sure some of these spectrum are available for the wireless industry and the society. Now, the second band, is, which I think is very important going forward, is a sub-terahertz band, right? Here, again, the opportunity is huge because we have more than 200 gigahertz of spectrum available from around 92 gigahertz to 300 gigahertz. A lot of them are really not used today. Of course, challenge is also enormous. Okay? We learned the lesson from millimeter wave. So this time around, if we want to explore these new bands, definitely we have to take them into account from day one. Higher path loss, right? PA output power is much less, efficiency is lower. And on the receiver side, LNA noise figure is much higher. And interestingly, as we have been working on this last few years, one thing that we never had to address, worry about, is a packaging issue. Because at those bands, at 140 gigahertz, the issue is when we build this RF modules, the antennas are so close to each other, there's no place to put the chips anymore. Because chip size is also like a few millimeters square. Where here, if you look at 140 gigahertz, the wavelength is about 2 millimeters. Typically, you put your antennas half a wavelength apart, right? Which is 1 millimeter. So if you think about it, where do you put the chips? There's no place for that. So that's a huge problem, actually, when we started to look into some of these new areas. But fortunately, we were able to leverage the collaboration with also a research community, in this case, UCSB, to solve some of the initial problems to build a prototype, which I'm going to show just in a minute. And then, of course, it's not all bad news, right? The good thing about those sub-terahertz and higher frequency band is naturally you have larger beam gains, right? Especially if you think about today, I think one of the lessons I learned is millimeter wave coverage is a big problem. One is the base station side, but also it's on the terminal side. It's very difficult to put 20 antennas on the terminal, even at millimeter wave band. Power consumption, form factor, they all come into play here. But if you go to these frequencies, compared to millimeter wave, naturally you can put many antennas and enjoy the beamforming gain, right? And another thing that, similar to this packaging issue that I mentioned earlier, right? The form factor and physical size can also come back and help you, especially if you think about this antenna in package kind of architecture. If you try to put this chip right next to the antennas, the front end, the output of the front end will be much closer to the antenna. So the feed line loss will be smaller. That's actually the plus side of this equation. So we do see this opportunity, still a lot of unknowns. Can we really develop technology to address all these challenges? Can we make it a reality as a good capacity layer? So only way to find out, of course, is to put them all together and test things out in the real life. That's exactly what we have been doing in the last few years in this area. So we have been collaborating with Professor Mark Rodwell from UC Santa Barbara. And he provided this 140 gigahertz RFIC, which is really one of the only RFIC available in the world for this band. And we built some modules and also communication systems around that to show indoor scenario. We did a test as well as outdoor scenario over a 2 gigahertz band. Okay, here you can see initial sort of a result are promising. We were able to show 12 gigabit per second at 30 meter and 2.3 gigabit per second at more than 100 meter, 120 meter actually. So still, I think a long way to go. This is a very line of sight condition. So very different than the actual deployment scenario eventually we're gonna do if we use that for access, not only for backhauling or FWA. But it's a good start. And every day we are working on that and improve that. Maybe I'll show a little bit more details. This is a video showing the actual POC setup. This is probably the first time we are connecting the CMOS RFIC with the indium phosphide PA, because at this band, CMOS PA, the efficiency is too low to give you the power and efficiency that you need. Okay. So a quick video clip to show the actual test that's happening in our lab. This is in our Dallas lab. This is showing the POC is actually doing this adaptive beamforming. So you can rotate the transmitter or receiver, and the system will automatically figure out the new direction to stay connected. Then there's a video showing the outdoor test. This is again outside of our Plano office. Okay, so hopefully this will convince you that there's potential, to use this band, and eventually as we put our minds together, work together, we should be able to overcome some of the challenges that we identify early on and make it more realistic. So moving on, the next group of technology that I want to quickly talk about is the duplexing technology. This is something that nobody really think about when we do the research, but that's very important. It's really talking about how did you separate the communication between base station to user and user to base station, what we call downlink and uplink, right? So really for the longest time from 1G to 5G, this kind of stayed the same. I mean, a lot of discussion happening for full duplex, but in the commercial system in industry, we always use either TDD or FDD. Maybe for the earlier generations, mostly FDD for the uplink coverage, better coverage, but in the later generations, 4G or 5G, as we start to looking into some of the new bands, for example, in the mid band or C band, then things moved more gradually towards TDD systems because more capacity, more bandwidth out there. I mean, it's good for capacity, but the downside of these TDD system is it hurts the uplink coverage, because the users has less chance to communicate to the base station. And for those of you who are in the industry for a while, when we talk about coverage of a cellular system, typically it's limited by uplink, not downlink. Because downlink, you can put large PAs there, but uplink, you are really limited by the tiny little PA that you can put on your phone. Right? So here, that's why, as I mentioned earlier, one of the things we learned from this 5G deployment is not only millimeter wave, but also C-band, we are suffering from the uplink coverage issue. So then that motivated something called cross-division duplexing, XDD. That's actually a part of active discussion in release 18 today. So idea is very simple. Moving from this TDD, you can see, right? TDD, you separate uplink and downlink in time, but in XDD, you borrow some part of downlink time slots and use that so that for uplink purpose. So a lot of users can continue their uplink communication, right? Therefore, you have better coverage. And of course, eventually, this is for 5G advanced. Hopefully, things will continue to evolve as we develop new technology, become a 6G technology of 4 duplex. So quickly put them all together, you can see the benefits, as I mentioned, is for better coverage. As we recognize, there's a huge gap between these mid-band TDD cells and lower band, especially lower band FDD cells. Okay? And the way to do that is to borrow some of the spectrum transmission opportunities from downlink slots to uplink. And while we do that, the problem is it creates what we call self-interference, right? Especially at base station side, if you think about it, because neighboring subcarriers or RBs are doing downlink. In the meantime, some of those opportunities in the middle are doing uplink because of a near-far effect, right? The downlink transmission power tends to be 100 dB higher than uplink reception power, right? Depending on how large the coverage is. So that's a very difficult problem to solve, and we have made some progress. I think eventually we should be able to get there, not necessarily to the level of reducing everything to the noise floor, but by combining several technology together, including antenna mitigation, including the digital SIC, should be able to bring them down to within a couple of dB of noise floor. So make this operation possible. So again, this is a quick video clip to show what we did. The second picture on the left, that's kind of a form factor of the test bed. So still, this is a separate antenna system. So transmit antenna and receive antennas are separate. We are not able to put them together yet. That's very challenging. Okay, so I want to move on and talk a little bit about the advanced MIMO technology, okay, as a next technology group. MIMO, especially FD MIMO, 4-dimension MIMO, is a 3GPP jargon. It's initially it was called Massive MIMO. Now I think everybody is calling it Massive MIMO. So that was a very important technology that drives 5G sort of growth in these new bands, mid-band, for example, provides very good capacity improvement compared to LTE days, right? So LTE, typically we have 2TX or 4TX system. But 5G with FD MIMO, we move into this, this area. We have 32 or 64 sort of transmit antenna systems, all digital, able to provide very good MU MIMO capability. So when we actually, interestingly, my team was probably first one to really quantify the amount of capacity benefit using a 32TX system about 10 years ago, using a very primitive channel model. At that time, I think our number is about 3 to 4. Interestingly, after a few years, the industry really come together and made a very sophisticated channel model and did a lot of simulation. That number did not change much. It's a huge number. 3x capacity gain is huge. If you think about how much money it costs per hertz or per megahertz to purchase some of the spectrum in these mid-bands. It's a huge amount of money, huge amount of benefit for the industry. So this is what we did, 3 to 4 times capacity gain using Massive MIMO. But going forward, one of the dimensions that we are thinking about is to actually separate some of the antenna elements in a more distributed manner. There are several reasons for that. One reason is FD-MIMO is good if users are spatially separated, so naturally you can form these multiple beams. But if you are clustered, like in a setting like this, many users are sitting together, especially if not too much reflections around to separate these users spatially, then the capacity gain becomes much smaller. So if you distribute those antenna modules around, for example, if you put them at 4 different corners of this room, then you have much better chance, right, to form a beam that can spatially separate these different users. That's one. And the other thing is, if you think about one of the key challenge for cellular industry is site acquisition, especially site that allows these huge, large base stations to be put up there and provide service. With smaller form factors, then you can expand available site. The rooftops, on the street poles and so on. So that's another motivation when we started looking into this. One is capacity, one is support of the support of the situation where the users are more clustered and also easier to deploy in the future commercial setting. So again, we did the initial sort of prototype and testing for this distributed MIMO technology. So what we did is we built like 3 or 4 RF modules. Each of them has 8 TX. Okay, then we set up a scenario where we put 6 users very close to each other and put 3 RF units. 2 of them are located together. One of them is a little bit separated, about 10 meters apart. You can see the results. It's very, very interesting. If you turn on one, it's about 60 megabit per second. If you turn on a second one, it helps a little bit, but not too much because they are next to each other. But then you turn on the third one, which is 10 meters apart. That really provides this additional spatial dimension. And all of a sudden, it here has a huge jump in the collective throughput. So it was very interesting learning, and we think going to 6G, especially if you think about this upper mid-band, right? We're talking about not only 64 TRX, we're talking about potentially hundreds of, even thousands of antennas. So ability to separate them and place them in a more flexible and modular way will be very good technology. Of course, there's a few key technology we have to solve. Some of it is how did you calibrate? That's actually one of the key things we solved during the course of this experiment. Calibration is very critical to exploit the uplink and downlink reciprocity for massive MIMO systems, right? But if all the antennas are together, you can imagine, you can put some circuitry there to allow this to happen. But what if they are distributed? How did you do that? So we actually developed something called UE-assisted calibration system to actually allow this to happen. If you're interested, definitely can share with you offline with some more details. So last, probably but not least, this is very, very exciting and important group of technology, and how do you apply AI to the 5G and wireless systems, right? So 5G and 4G, we are already seeing a very good set of use cases, early successes using AI technology, not only from the terminal side, but also from network side, right? So here I want to share a few use cases. Some of them are actually commercialized that my team worked on. For example, 2 or 3 years ago, we worked on this early application of reinforcement learning to do a very simple task, to decide when to switch between Wi-Fi and cellular, right? Because everybody has a different preference. Just imagine you are leaving your house in the driveway. Do you stay with your Wi-Fi a little bit longer, or do you cut Wi-Fi and then move to cellular? So we found that using this learning algorithm, we can much better understand the user's preference and make a more intelligent and better choice. So that was actually won the WBA Industry Award in 2019, this work, together with Wi-Fi 6. And then recently, last year, we're looking at how do you adjust Wi-Fi parameters so you can save power. Basically, Wi-Fi is a little bit more flexible compared to cellular systems. At the terminal side, you can adjust some of the parameters, for example, the wake-up time, and when you wake up, how long you stay awake, right? So you can imagine, right, if you are just doing some web browsing, it's not so important for you to stay awake all the time for the Wi-Fi modems. So it's better to put them to sleep and wake up very infrequently to save power. But on the other side, if you're playing a game, you want this to be awake all the time, so because otherwise it will be a huge latency. So what we did is actually we developed these AI algorithms to learn the service type. Right? So actually you may ask, we are the phone manufacturer, right? We make the smartphones. Why do you need to know what is a service type, right? But the thing is, there's tens of thousands, millions of apps out there. Even though we know the name of the app, we don't know what it's doing. And also a lot of times, even within one app, there's several sort of different type of service that's being provided. So that's why it's important to know that. We use AI to learn the service, and then on top, use that knowledge to set these Wi-Fi parameters. The result is very good. We are able to save about 30% of power from that Wi-Fi modem, and we commercialized that last year. And there's good applications on the network side. One of the examples is self-planning. We use this AI to predict the path loss. Otherwise, you have to do a lot of very heavy lifting, sort of a ray tracing task. It costs a lot of time and power and money to do that. Okay, so still lots of good applications, especially network side, we can see that's happening. But since we're talking about 6G, so then the natural question is, how is it different? What's happening now in the terminal side, in the network side, in 5G, compared to what we see it's going to happen in 6G. So one way to look at it is what we are doing today in 5G AI application is what I would call local AI, because standard is already there, so you can do optimization individually or separately at mobile phone side, at base station side, core network side. Then going forward, Release 18, 5G Advanced is already looking at how to combine them together, what I would call, it's a very simplistic view of looking at what's happening. But if you have ability to jointly train some of the models, looking at the data from both base station side and the terminal side, then you can do better. That's what we're doing. For example, some of the CSI feedback optimization tasks that's happening in 3GPP today. And then if you look at further into the future in 6G, then you really think about holistically comprehensive end-to-end AI application to really integrate everything together and provide the best performance. And another thing I think people ask a lot, especially when you think about AI, why AI? Communication system is well designed. Well, why do you think AI can do better, right? So we actually also did a lot of soul searching. I mean, this summarized a few of our intuitions in a few simple words. One is AI, as you can see here, provides a better global awareness of the situation. And second thing is AI is naturally better. If you want to do something across different functions and layers, you can blur the lines between these different functions. And third one is handling nonlinearity and long-term correlation. So there's a lot of good ideas behind that. Probably can talk more later offline. There's a few good examples of what's happening, especially if you think about AI native design, encoding, modulation, spectrum sharing, and CSI feedback. I'm sure the group here will come up with a much more diverse set of ideas to take this forward. And not only for the physical layer and radio design, but we also think this using AI for network optimization will continue as we are doing in the 5G days. Especially, I think one very important area to look at is to use AI to optimize network across different time scales. That's a very important aspect because in the network, the optimization and operation happens at different time scales. Some at schedule level, it happens at millisecond level. Right? Channel estimation, transmission mode adaptation, and so on. Some of them happens at much slower time pace. So how did you come up with AI algorithm to more naturally integrate these different tasks together? Okay, with this, probably share a bit of the what we think will be a reasonable timeline. Of course, this is still a part of a discussion. across the whole industry and the research community. The end goal is trying to come up with a 6G specification, both from the 3GPP side, but also from ITU side by the end of this decade, right? Then if you break them down, in 3GPP side, we still have probably a couple of years left to do technology preparation. Then sometime around 2025, we'll really pick up speed to do study item and really just have time for 2 work items. So end of decade sounds very far away, but when you break them down, really we don't have much time to do this initial technology preparation and develop the key know-hows, enabling technology to solve the challenges that we saw in some of these different bands. I mean, the good thing is, in this time around, compared to 5G days, I'm really happy that there's much better awareness across the world, right? In the United States, we have NJ Alliance. I know some of the key leaders are here today with us also, Amitabh, Ting-Fang, and also RING's program, and also very good examples in Europe, Asia, and ITU is taking action. I think this is not the case in the early days of 5G. So I think really that's one big lesson we all learned from 5G, that you have to start early, you have to work together as a community to prepare and to overcome these challenges. So with this, I would like to finish my talk. Again, thank you very much for inviting me here, and I look forward to good collaboration with all of you through the 6G at UT. Okay, thank you.